Hello and welcome to another Glencore Technology webinar. Today's webinar is More from Less with Jameson Concentrator. Your presenter is Gabor Chichovsky. There will be questions and answers straight after the webinar, so please feel free to use the Q&A button at the bottom of your screen at any point during the webinar or immediately after. Ignore the raise hand icon. That's it. Let's enjoy the webinar. It begins now.
Thank you, Stephen. The title of my webinar today, More from Less with Jameson Concentrator, or How the Jameson Concentrator Changes Traditional Concentrator Design. The topics I would like to talk about today are as follows. First, a Jameson Concentrator 101. Then I would like to address some questions asked by the industry, show you some trade-off studies, a Jameson Concentrator case study, and some interesting recent test results. So first, Jameson Concentrator 101, or how bubble size affects flotation kinetics. So let me quickly introduce the Jameson Cell. So the key principle and the heart of the whole Jameson Cell technology is the Dunkamer. So what happens in the Dunkamer is high-pressure slurry is pumped through an orifice lens, and that slurry jet hits the slurry in the Dunkamer and creates a plunging jet and a high shear and mixing zone. And also in the same time, it entrains air. So because it entrains air, it creates vacuum, and that's why the Jameson cells can operate without a blower, because they self-aspirated. In the high shear mixing zone, very fine bubbles are generated. So on the graph on the right side, you can see how the size of the bubble generated in a Jameson cell compared to other technologies. So it's very fine compared to mechanical cells or column flotation cells. And also another interesting feature is that with increasing the air rate or the superficial gas velocity, the size of the bubbles hardly change, so they stay quite reasonably constant. So how the bubble size affects flotation kinetics. So on the left side, you see this equation, which is basically how the bubble surface area flux is calculated. Now you can see that the lower the bubble size, the smaller the bubble size, the higher this bubble surface area flux. And the higher the bubble surface area flux, the higher the flotation kinetics. So that's how it is interconnected, and that's how small bubble size can actually affect flotation kinetics, and small bubble size enables the Jameson Cell technology to provide and offer very fast flotation kinetics. Now, on the next slide, I'd like to highlight another interesting feature of the Jameson Cell, which is the wash water capability. So when the Jameson cells use wash water, the wash water washes out the entrainment, the gangue from the concentrate, and it upgrades the grade of the concentrate with this wash water feature. So this upgrade is usually equivalent to three stages of mechanical cell cleaning. Also, another important feature of the Jameson Cell is the high carrying capacity. So what it means, it can produce much more concentrate on the same footprint than other flotation technologies. So the key takeaways are, one is the wash water capability of the Jameson Cell, and the other one is the quick and guaranteed particle bubble interaction, or other words, the fast flotation kinetics. Now, how do we design a Jameson concentrator? So first, we take test work information and compile a grade recovery curve. So you can see at the bottom of the slide a typical grade recovery curve. Now we split this, and what we do is we're trying to achieve a final concentrate grade in the first step, get the fast floating, highly liberated minerals that are present on the left side of the grade recovery curve. So we're trying to scalp off these highly liberated minerals in the rougher scalper duty. First with deep froth level, low air, high wash water ratios. Now what remains is the middlings, the slower floating minerals in the tails of the rougher scalper unit. So that those minerals are actually recovered in the next stage, which we call the scavenger stage, where we're trying to maximize recovery. And the way we do that is we use shallow froth levels, low wash water ratios or no wash water at all, and high air pulp ratios. So yes, we're trying to focus on that right part of the grade recovery curve, to the middlings, the lower liberated minerals. So again, main approach is we split the grade recovery curve. First, a scalping phase to focus on the grade, and the second stage is maximizing recovery. So it's also important to mention that Jameson cells actually scale up one-to-one from laboratory scale results with high accuracy, but I'm going to be talking about that a bit later. Now, looking at this from the whole circuit perspective, this slide shows you how parts of conventional cells and conventional circuit are replaced by Jameson cells. Now, if you look at a typical a base metal or copper flotation circuit, let's say you have a rougher scavenger bank, which comprises of typically 6 mechanical cells in a row. So now we would say that first of those 2 cells would be replaced by a rougher scalper flotation cell, Jameson cell, and we would produce a final grade con. The remaining 4 cells would be replaced by 1 scavenger Jameson cell that would be focusing on the recovery. So the downstream processing of the scavenger concentrate, again, in a conventional circuit, it happens, let's say, in 3 stages of cleaning. Now, in the first stage, again, similar idea, we would split it between a cleaner scalper and a cleaner scavenger cell. And the cleaner scalper cell would produce a final grade concentrate, and the cleaner scavenger cell, again, would focus on the recovery. So next, in the conventional circuit, there are another 2 recleaning steps. So because of the high efficiency of the Jameson cells and high upgrade ratio, we could actually replace those 2 stages with only 1 recleaner step with a Jameson cell. So as you can see, there's a massive reduction in the number of equipment, a number of flotation cells, which contributes to the high efficiency and the low footprint of the Jameson concentrator. So what is a Jameson concentrator? What is this whole concept? It's a compact, high capacity concentrator design. It reduces OPEX, CAPEX, it reduces footprint and height. Also, it decreases carbon footprint and increases the recovery of fines. It offers flexible flow sheet configurations. We also have easily transportable modular designs, and it's based on well-proven high-performing technologies such as the Jameson Cell and the isomeal technology. Now, in the next few slides, I'm going to be talking about some questions asked by the common questions asked by the industry. So first, very common, very typical, are Jameson cells suitable for rough scavenger duty? So while most people are aware that Jameson cells high performance in only aware of the high performance in cleaning duties, many people are not aware of the good performance in rough scavenging applications. So now look at this example. This is for a major copper project in the CIS country, and we did a pilot test over there on site with a feed particle size of 74 microns P80. So very typical rough scavenger application. So first we ran the feed through just one stage rough scalper duty, and then we ran the same feed through a rough scalper and a scavenger duty. So in both cases, in the rough scavenger duty, we had almost 90% copper recovery at pretty much final grade concentrate. And in the second test, where we had Jameson Cell, we used a Jameson Cell on these tails of the rough scalper unit. We added an extra 7% copper recovery. So all up, 94% copper recovery. That was well above the target recovery that was defined by the client. And also, for your information, there was a parallel test work and with mechanical cells, and we matched the same recovery with only two stages of Jameson Cell flotation. Now this is the same pilot, so just some videos from the pilot. What you can see is the rough scalper application producing a very high grade concentrate. You can see that from the color. Next, this is the scavenger cone, so it obviously looks more barren, but still has reasonable amount of copper. And then the last video is showing the scavenger tails and the cone on the right side. Okay, so another study, another pilot test work in Australia, actually, on a site in Australia. So about 2% copper feed. And actually this is an operating site, and they have 6 mechanical cells in a row in the rough scavenger bank. So what we did, we took a sample from the same feed that feeds into the rough scavenger bank, mechanical cells, and run that through 2 stages of Jameson Cell pilot rigs. So first stage was a rough scalper and again a scavenger duty. So what you can see is that we achieved 95% recovery in total compared to 93% copper recovery actually with the mechanical cells on site. So that was the actual site performance, and we added an extra 2%. Also important to mention that because of the high upgrade ratios in the Jameson Cell, we managed to cut the mass pool to the cleaners to 0.8% of the feed, whereas the site mass pull was 9.4% in the rough scavenger bank. So what it means is obviously it would be a much lower, a smaller load on the regrind and the cleaner circuit. So again, what you can see here is 2 Jameson cells replace 6 tank cells. So on this next slide, I could go on, but I'm just trying to summarize all other results from other sites. So these are 6 sites, operating sites, and with target concentrate grade. And this is a Jameson cell in a rougher scalper duty and the performance of the Jameson cell. So you can see is that we managed to get and obtain final grade concentrate, so basically above target at usually 60, 70, even at 80% recovery. And these are all rougher feed, Jameson cells on a rougher feed. So yes, we have a lot of experience actually Jameson cells running on a rougher feed. Now the next question that's also that is also asked is, can Jameson cells float coarse particles? Now let me show you some examples here. Again, this is a recent test work with an L150 Jameson cell for a major copper project. So the feed size was P80 180 microns, so quite coarse, if you agree with me, and about 0.7% copper feed. So we ran that through in a batch mode through the L150 Jameson cell, and we had 10% copper grade at over 90% copper recovery. So the same feed through a band scale flotation equipment unit, mechanical cell, a bit smaller, lower recovery, so 89%, and much lower grade. Now, this is another separate test result that was produced at an Australian copper operation. So they did a size-by-size copper recovery, and you can see the results here. So with the normal standard downcomer, what we achieved is you can see it's a typical elephant curve. So a bit lower recovery on the coarse and the fine size, but basically we were quite close and very typical to mechanical cells in the coarser grind size, so like that plus 200 microns. So we had a bit lower flotation rate, but it's also very typical for mechanical cells. So we were actually matching that performance that mechanical cells can offer in that coarse range. However, we had a much higher performance in the fine range. So the minus, for instance, minus 5 micron range, that was much better performance than you can see with the tank cells. And with the alternate downcomer, that's a new development for the Jameson cells. Our coarse recovery was even better. So yes, what we can see here is Jameson cells can actually match the coarse side of the particle distribution and can match the coarse recovery of mechanical cells, while definitely Jameson cells can outperform the fine range the fine recovery of the mechanical cells. So the next and last question that I usually get is, why can Jameson cells be scaled up directly? So if you look at a conventional circuit design, you usually start with a bench scale flotation test work, let's say a 2-liter batch flotation cell. You plot the grade recovery curve, and you use because of some hydrodynamics reason, use a scale-up factor of 2.5 to get to the full-scale residence time from the lab scale residence time. Now, when we carry out a laboratory test work with Jameson cells, or a simulation with we call it the three-stage dilution cleaning. So what we see is the results directly scale up 1-to-1. So these are all these graphs are showing results of dilution flotation tests, and then plant surveys on a Jameson cell, which was later installed on site. So you can see they align very well, and yeah, there's no real gap or big variation. So the results that we got from these dilution tests, they were very accurate, and we could produce and reproduce that on a full scale. So now this is another pilot test work. This is a pilot test work actually, not a dilution cleaning test work. So a pilot test was run in a large copper gold application in Australia, where at different feeds, where we plotted this grade recovery curve. You can see the red dots and the green dots. Now, the client was happy with the results, and they installed a Z8500 12 downcomer unit, which was commissioned in 2022 on site. And the site performance was basically, again, matching what we achieved with the L500 pilot Jameson cell. So now I'd like to show you a very interesting trade-off study that was prepared by Osenko. So Osenko undertook a trade-off study between a conventional and a Jameson concentrator. So obviously same process design criteria for both circuits. The conventional concentrator and the Jameson concentrator all 40 million tons per annum tonnage, and it's a copper circuit. So they ended up with for the conventional circuit with a large number of flotation cells, whereas for the Jameson concentrator it was only five flotation cells. So now you can see that the footprint difference was massive, as you would imagine, 56% reduction. And also there was a height reduction of about 33%. Now, the same study, if we dig a bit deeper, we can see the reduction in concrete and steel. So you would imagine and assume that if you have less equipment, you would need less concrete and steel to install for installation. So now you can see that on the left side, it's the structural and equipment steel that's required for both options. Now, the Jameson concentrator cut the steel consumption by over 70%. And as for the concrete, the Jameson concentrator was or required 45% less concrete for the installation. Now, look at the capital costs. Obviously, these savings in steel and concrete all drive the savings in the capital costs. So this capital cost was estimated to a minus 20 to 30% level in accuracy. And it turns out that the Jameson Concentrator can save about 25% in direct costs for this project compared to a conventional concentrator. Now, what I like to highlight here is when you want to quantify, you want to use a factorized approach to get to the capital costs. It's not well suited for the Jameson Concentrator, so it's actually crucial to quantify steel and concrete costs when conducting a trade-off study, because it has a significant, because structural costs have a significant impact on the CAPEX. Now, talking about power consumption differences in the next slide. So the Jameson Concentrator was able to reduce power consumption by 36%. And it comes by, it's basically enabled by not using blowers, and also there's no need for mixing that many mixing mechanisms, because Jameson cells don't use mixing mechanisms, and there's only a few Jameson cells. So yes, you'd need pumps, but again, feed pumps for the Jameson cells, but there's a massive reduction in flotation cells. So altogether, the trade-off is that your power consumption is much less with Jameson cells. And yeah, the last interesting conclusion was the carbon emission. So you can see yearly operational carbon footprint with the dark blue, and the light blue is the construction footprint. So in both carbon emissions, the Jameson Concentrator was much more efficient. 56% savings emissions during construction with the Jameson Concentrator, and about 30% savings over the life of mine. So in the construction phase, obviously, the savings are coming from the fact that you use less steel and less concrete, which all need carbon, and you need to burn carbon to produce steel and concrete. And in the operation phase, the savings are mostly coming from the reduction in power consumption. Now, I would like to show you some case studies on Jameson concentrators that are either running or in the construction phase. So first, this is the New Britannia concentrator of Hut Bay in Canada. So this full Jameson concentrator was commissioned in 2022, and 11 tank cells were again replaced by only 4 Jameson cells. It offered right away 50% less footprint and power consumption. It was commissioned very quickly and achieved TS target within basically 24 hours. Now it's currently operating at or above design grade and recovery, and with the client we've published joint papers many times, and yeah, we've got a good relationship with the client, and they were so happy that they already installed another 5 Jameson cell at the other concentrator called the Stahl concentrator in 2023. Now this is another project where the client went for a Jameson concentrator. This is a lead and zinc project, a major lead and zinc project. And as you can see, it's in the construction phase. As you can see, 19 Jameson cells replaced against 63 tank cells. So you can see on the right side the 3D models and the massive savings in footprint. So it was about 50% footprint savings, and also in power. Again, there was a reduced height, no air blowers. We can say it's also a safer design because the lower heights and no confined spaces are required, and also significantly fewer spares. Now, this is a video of this lead and zinc concentrator in the construction phase. So you can see our big B8500 flotation cells. So the whole circuit, and then the cleaning circuit. And you see the regrind isomills. Another project that we've been just recently awarded with is the Hermosa project by South 32. So it's a 4 million tons per annum lead and zinc concentrator in Arizona, US. We were awarded with a contract again this year, and it comprises of 4 B6500 cells for lead and zinc roughing, 3 8 downcomer cells for lead cleaning, and 3 B4500 12 downcomer cells for zinc cleaning. Now, when we asked the question from the client why he picked the Jameson concentrator, he had the following answers. So it maximizes fine recovery using proven Jameson Cell technology. It minimizes plant footprint, which was a high priority in the design. It reduces plant energy consumption by about 30%. And it also improves the safety of the plant by eliminating the need for people to be exposed to confined spaces or working at heights. Now, this is another project we're still bidding on. It's a major copper project in the CIS region, 60 million tons per annum throughput. So our offer is you can see on the left side, again in footprint, compared to the right side of a conventional circuit. So differences are quite significant. Now, I'd like to show you some interesting recent test results. 60 million tons per annum Jameson Concentrator gold copper project in the Eurasia region. So we did some pilot plant test work with L500 Jameson cells. So the circuit recovery was over 90% at about 19 to 20% grade at different grades. So and it's a full circuit. So very good results. Again, final grade concentrate at that high recovery. Another project, the Aero Copper Caraiba project in Brazil. So there was a pilot test work carried out at Caraiba, which showed that 70% or 80% recovery of copper at final concentrated grade of almost 35%. So the client was so happy about the results that they bought a Jameson Cell in a roughest copper duty, and they commissioned it commissioned the full-scale cell this year. Another interesting test result that was carried out in Australia at Triton Mine. In this case, the aim was to prove that the Jameson Cell could achieve high recovery, again, the L500 Jameson Cell was operated and operated over several days to get different sections of the grade recovery curve. And we actually, with the Jameson Cell, reached and exceeded the target final concentrate grade 25%, which was 27%, at 80% recovery when we ran the cell optimally. So the pilot rig results matched the results of the three-stage dilution cleaner test on various ore blends. And finally, I'd like to summarize the key takeaways from this webinar. So the Jameson Concentrator is a safe and environmental and sustainable solution for the mining industry to meet the needs of the future. It reduces CAPEX and OPEX. It demonstrates very good performance in rougher duty, even with coarse feed. It has an accelerated design with one-to-one scale up from bench scale to full scale with very high confidence. There are also 3 Jameson concentrators operating or under construction. There are close to 50 Jameson concentrators in the sales pipeline, seriously considered by clients for projects in the next 5 years. And just for your information, GT Glencore technology offers Class 5 and Class 4 estimates in the early phases of projects, just to help the client understand the CAPEX and OPEX of the projects. And with that, we're not competing with EPCMs. We work with the EPCM selected by the customer, and we just want to provide equipment. So and that's it. So thank you for everyone's attention today, and I would like to know any more regarding our technology. If you'd like to know any more regarding this technology, please email the addresses shown at the bottom of the slide.
Thank you, Gabor. And thank you for coming along to our webinar. That's it for the main content of the webinar, but we will stay live on air for a few more minutes answering the questions that you may have. Just use the Q&A prompt at the bottom of your screen. In a few days, you'll get an email with a copy of the webinar and indeed the questions and answers that were asked and answered. That's it. Thank you for coming to the webinar. We'll see you in the next Glencore Technology webinar.